So, welcome back. So, before taking up the Cauchy linear case, so let me just show you some slides. So, here collected all the things I said about the linear case. So, that non-characteristic condition on the surface. Okay, so, this characteristic form, and then we define this characteristic set or variety, and so we defined what the characteristic surface and non-characteristic surface. Again, if you go back and see the condition that non-characteristic condition. So, this unit normal should not be perpendicular to A x, that vector A, and then that you translate into the this parametric functions h 1, h 2, h n defining the surfaces, and you arrive at this determinant condition. So, this determinant, so you replace the, so this is n by n minus 1 matrix. So, you just add one column here A 1, A 2, A n, again restricting the values to the surface, because H s is on the surface. So, now you get an n by n matrix, and this determinant should not be 0. Okay. So, this is the analytic statement of S being non-characteristic. Okay. And then you just form these characteristics, and then the given differential equation also is converted into an ODE on the characteristic, and you derive you show that these are all you can solve all these ODEs, and then again you get back your solution using inverse function theorem, using the non-characteristic condition. Okay. Similar thing for Cauchy linear equation, it is almost same, but now only thing is the coefficients A I, they may also depend on u. Okay. So, that is how, that is why this system of characteristic equations, first order system of ODEs is incomplete, because the right hand side also depends on u, and so we have to somehow adjoin that, and that procedure is called, again, given the surface you lift it to the n plus 1 dimension, and there you define S tilde, and again the non-characteristic condition becomes so same thing as you see here, but now these are also functions of u. So, that you have added, and this condition is on S tilde. Okay. But in any case S tilde is obtained by S by the lifting, and you get again this non-characteristic condition, and again the same procedure, you solve a system of ODE and again apply implicit function theorem to get back the solution. Okay. It is exactly similar to the two variable case. Okay. So, let me just explain this procedure Cauchy linear case using some examples. Examples are always better. So, Cauchy linear case. So, the first example is Burger type equation. So, again let me use the variables as t, au, ux plus bu, uy. You have already seen this part, that means only in two variable, and you have seen that, for example, if you take a equal to u. So, in comparison with the linear equation, so however smooth the initial condition is, we see that the solution develops singularities at a finite time. Okay. So, similar phenomena we observe even in this two dimensional case. So, x y belong to R 2. So, this is Cauchy linear equation because a and b, they depend on, the coefficients depend on u. Okay. So, let me again use the variable t itself as the parameter for the characteristic. So, whenever convenient, we should do that instead of going for the, yes, of course, to develop a general theory we have to develop in that way, but in a typical example like this, if some parameter, some variable, if it is possible to use one of the variables itself as a parameter, we should do that. So, given this thing, so we would like to, in principle we try to find solution for all t positive, and let us see, just like the Burger equation in 1D, whether this solution develops singularities or not. Okay. So, here the characteristics again. So, dx by dt is equal to au, dy by dt equal to bu. Of course, since u itself is unknown, we cannot solve. Okay. So, that is how we adjoin that u also. In this case, you immediately see that du by dt along the characteristic is 0. Okay. So, this is very easy to solve. So, this is just u equal to, because it is a constant, u 0, and so that means again just see that we are abuse of notation. Okay. Y 0 0, and that is given as u 0. Let me call this as x 0 and y 0. So, this is x 0 and that is y 0. Since u is constant along the characteristics, we can also integrate these two equations. So, let me write that. So, x t at t equal to 0, it is x 0 plus t a u. So, let me write that, because that is a constant, and we know that what that constant is, a of u 0 x 0 y 0. Okay. And similarly, y of t is equal to y 0 plus t b of u 0 at x 0 y 0. Okay. Our task is, so again by this also is straight line. So, let me just draw that. So, this is the x y plane, and this is t x. Okay. Now, our next task is, so this starting anywhere x 0 y 0. So, this is the plane x y plane, and that is t equal to 0 there. Okay. So, this is a straight line. So, this is C characteristic. Okay. Now, our task is to find the solution. So, given any x y t, t positive, we should be able to draw a characteristic meeting the x y plane at x 0 y 0, and then we should be able to at least figure out what x 0 y 0, and in that case we have x y t, because u is constant along the characteristic. Okay. So, given this x y t, if this x 0 y 0 is unique, then we do get the solution at x 0 y 0. Just like the Burger's equation in the one dimensional case. So, our task is, so now consider these equations t a u 0 x 0 y 0 and y zero. So, task is to find x 0 y 0 in terms of x y t, and these are nonlinear equations. So, we will not be able to find them explicitly, but the implicit function theorem comes to our rescue. Whether such a thing is possible or not, even that we are not able to decide just by looking at these two equations. So, we have to apply implicit function theorem in order to find out whether x 0 y 0 from these two equations are expressible in terms of x y t. So, we want to solve these two equations for x 0 y 0 in terms of x y t, and that those are given to us. So, given a point x y t, we want to find x 0 y 0, and and then the solution is given by this. Once we find x 0 y 0, the solution is given by that. Okay. And what does the implicit function theorem tells? So, you look at the determinant of the Jacobian. So, determinant. So, this is a 2 by 2 thing. So, let me just write it. So, 1 plus t a prime at u 0 x. So, everything evaluating at x 0 y 0. So, let me just write once and then I leave it. So, del u 0 by del x 0 t b prime. So, here the derivative a prime b prime are with respect to that corresponding variable, namely dA by du, dB by du, and this is del u naught by del x naught. And similarly, here t a prime del u 0 by del y 0 1 plus t b prime. So, there should be b prime del u 0 by del y 0 should not be 0. Then the implicit function theorem tells us that x 0 and y 0 are expressible in terms of x y t. And what does this condition? So, this is just 2 by 2 matrix. So, we can easily determine, and this is 1 plus t b prime del u by del y 0 plus a prime x 0 should not be 0. In case of one variable, we have only had one term. Now, both the terms are combined here, and at t equal to 0, this determinant is 1. So, certainly not 0. So, we can expect this to be non-zero. This means this left hand side. For small t positive. Of course, if this term in the bracket remains non-negative, so similar to the one dimensional Burger's equation, this is always true, but when that changes sign, then there is a finite time when this becomes 0 and the solution becomes singular there, okay, namely its derivative vanishes. So, similar to the Burger's equation in one dimension, a theory can be developed for this also, and even higher dimensions, same procedure, but a single equation, and so you just like Burger's equation, we continue the solution for all time as a weak solution, all those things. So, all that theory can be developed here also. My second example, again a Cauchy linear equation similar to Burger's equation, but now we have something different there. So, x plus u du by dx plus y plus u du by dy equal to 0. So, examples tell us there are many different situations. So, we saw in that Burgers type equation singularities will develop, but here we see in this particular initial value problem, again t equal to 0 is a non-characteristic here. So, you should take different initial conditions and try to see what happens. So, this is also Cauchy linear, because the coefficients depend on the solution u. Okay. But now there is an x there, there is an y also. So, the coefficients also depend on x and y. So, again the characteristics. So, dx by dt is equal to x plus u and dy by dt is equal to y plus u. Okay. And similar to the previous example, we also have du by dt equal to 0. So, that implies again like previous thing. So, x 0, y 0, 0, and this is by the initial condition. So, this is just x 0 plus y 0. So, x 0 y 0 are the initial conditions for these two equations. Okay. So, plugging in this extra information we got in these two equations and integrate them. So, it is very easy to do that. So, we get x is equal to x 0, let me just little computation. So, just I write it here, x 0 plus, so let me call this as u 0 for simplification. So, u 0 e to the minus t minus u 0. So, you integrate this. So, it is no more a constant, but there is an x term. So, that is how you get that exponential term. Okay. So, and similarly y is equal to y 0 plus u 0 e to the minus t minus u 0. So, again given x y t, a point with t positive, we want to see, now this is no more a straight line, it is an exponential thing is there. So, it is a curve, characteristic curve, and you want to find out the characteristic curve meeting the xy plane. So, this is t x y t, t positive wherever it hits. Okay. From these two equations, it is easy to solve for x 0 y 0, but we do not need that. What we need is x 0 plus y 0 together. Okay. That is much easier to obtain. So, just little algebra, I just leave it. So, this implies x 0 plus y 0 is equal to x plus y divided by 3 e to the t minus 2, and therefore get u x y t So, this is also Cauchy linear equation, but we are able to find an explicit representation of the solution, which is valid not only for all x y, but all t bigger than or equal to 0. So, just because an equation is Cauchy linear, we should not say that it will develop singularities at finite time. So, here you do not see any singularities, okay. It is very smooth. So, obviously, some effect is coming from addition of these two. Okay. So, now let me again from this move on to the fully nonlinear case. So, nonlinear equation. Of course, this even in 2 dimensions you have seen is quite complicated. So, it required the introduction of more geometrical objects like Monge cone, characteristic strips, and so many other things. So, you can expect same difficulty to continue even in higher dimensions. So, this x u p. So, this is how we started. Okay. Again non characteristic Cauchy problem. Okay. The same theme as in the case of 2 variable continues. So, you again describe the characteristic equations, and now you have n equations coming from the for the x variables and one from the solution, and then there are n equations coming from the first derivatives. This was not there even in the Cauchy linear case. Okay. So, these are additional things. Now, there are 2 n plus 1 equations and 2 n plus 1 unknowns. What I would like to draw your attention is to this strip condition, and so this is the strip condition, okay. And we have this see this variables p I. So, we have obtained ODEs for them, but there are no initial conditions for them, okay, p i's. So, the for initial conditions for this x, we can take it a point on the given surface, and initial condition for z comes from the initial condition imposed. So, initial condition for x and z, there is absolutely no problem, but for p there is no initial condition. So, we cannot really solve this set of 2 n plus 1 ODE, and we are assuming that there are functions which qualify to be initial conditions for the p equations, these p equations. Okay. And this is a restriction on the function f. Okay. So, that I want to write it. Okay. So, here the initial conditions. So, I want to make a comment on this initial conditions on PIs. Okay. So, they are assumed in the form this x 0 s, s is parameter on the surface, and u u0 s and then p0 s. So, this you should remember. We are assuming, so these are known. These are known. These are unknowns. So, we are making an assumption that these functions exist, so that this equation is satisfied, plus the strip condition, that is also important. So, namely du 0 by ds equal to p 0 dx 0 by ds. These are okay, this let me n case. So, just let me write it in one go. Summation p 0 j s dx 0 j by ds. We are assuming the existence, assuming existence of P01 and these P01, P02, P0n, they serve as initial condition for ODE of PI. Okay. So, then the system of characteristic equation complete, and in general it is very difficult given a situation. In some situations we can easily decide whether such functions exist or not, but in some other case it is very difficult. Okay. So, I would like to illustrate with some examples. So, this example is very simple. So, I take in two variables, just two variables. So, instead of P1, P2 I am using PQ. So, we can immediately conclude no solution. As we are seeking only real solution, we can immediately, so two variable case, let me mention that. Let me illustrate with another example So, where it becomes so difficult, why a certain equation has solution, and so this depends on the initial condition also. So, just remember here, okay, the given equation is involved and something else is also. Okay. So, another example. So, u x square, again 2 variable, let me write it. So, this you can extend it to more than 2 variables. I am just taking a simple equation. I will come to the initial condition little later. So, this implies, just by looking at the equation, u x at 0 0 equal to u y at 0 0 equal to 0. At the origin, so this right hand side is 0 and these are squares, they also must be 0. Okay. So, we can try a function of the form whose first derivative at the origin vanish. So, this is some quadratic. So, we can try that. So, constant I can add, that will not affect the equation at all. So, the C 0 is a constant and we will assume a quadratic function. Okay. So, at least these conditions are satisfied by this thing. So, then we have simple calculation. So, this is just a x plus b y and u y is b x plus c y. A, B, C are constants. Okay, I am just taking them constant. So, you can see that this u x square and u y square, if we do not want the cross term, namely the x y term, okay, so we should have, so this is just comes to be. So, let me write it, simple calculation. If C is equal to minus A, you take C equal to minus A and you see that the x y term gets cancelled, x y term comes here, x y term comes there. So, that get cancelled and you have this simple expression, and this is equal to x square plus y square if a square plus b square equal to 1. Okay. So, that let us call that a equal to sin theta, cos theta, or okay, sin theta, right. So, you can check that. So, u x y is a solution, it's constant half cosine theta x square. In fact, you can now take plus or minus b x y minus half cosine theta y square. And suppose we, so there are two solutions, you see immediately there are two solutions. x 0 is C 0 plus half cosine theta x square. Okay. And just observe this coefficient here. So, if the absolute value is always less than or equal to half. So, this on y equal to 0. So, suppose, so this solution satisfies this initial condition. So, my question now is, can we take u x 0 some constant, say any constant. So, constant we see that it is not bothered, minus x square or C 0 plus x square. Answer is not easy. So, I want you to study this example in carefully, and you see this is decent looking equation and decent looking initial conditions, okay. Yet it is difficult to see whether it has a solution or not. So, it only shows that the method of characteristics still has some mystery which are not revealed in full. So, in particular the study of first order equations, there are still some gaps. So, because we are not able to say completely that such an equation, okay, very decent looking equation with some conditions like this, initial conditions, whether it has a solution or not. Okay. So, with that I come to an end of discussion, this discussion on nonlinear first order equations. Nonlinear equations are really difficult. So, you have to study them very carefully, and even in simple examples you see we face difficulties. So, try to do these things by method of characteristics and see the difficulties yourself. Thank you.